So notice that when we have a first order equation written, whoa, so notice that when we have a first order equation written as y prime equals f of xy, this is actually a recipe for the slope at the point x comma y. Oh, I guess that's a little typo. That's supposed to say at. There we go. So that means that if I look at a particular point, so I pick a particular x, y, and then I plot the slope there as a little line segment, it'll produce what's called a slope field. So this looks sort of like a vector field, and it's kind of a graphical picture of what the solutions to the differential equation look like. So suppose we do this for some examples. Like let's take dy dx equals, and we'll just do say 1/2 y. All right, what does that look like? Well, here's my axes that I'm going to sketch this thing on. And so then I'll pick some point xy, and at that point I will look at f of xy, which in this case is just 1/2 y. So let's see. So say I look at the point 0, 1. All right, then my corresponding slope is going to be y over 2. If I look at 0, 2, then my corresponding slope is going to be 1. If I look at 0, minus 2, then it's going to be minus 1. If I look at 0, 3, then it's going to be 3/2, and so forth, right? So now I'm going to take these numbers and let's see. So the point 0, 1 is this guy right here. And so I will draw my little slope of 1/2, so over 1 and up 1/2, so like this. Okay, and then when I go up one more to height 2, then I now have slope 1. And when I go up again, now I have slope 3/2, and then slope 2, and things start to get steeper and steeper. Meanwhile, if I go down below, then I have minus 1/2, minus 1, and minus 3/2, minus 2. And I forgot to compute it at 0, 0, but you can see that it's just going to be 0 at that point right there. Now, how do any of those computations change when we move to a different x coordinate, like say x equals 1 or something like that? Well, they don't change at all because the calculation was completely independent of x. So let me just re-sketch what those slopes would look like if I were to move over a notch. They would look like this. And that's the same as if I moved in a negative direction as well. And so now we have a slope field. Okay, and so then the solutions to this differential equation are going to be the curves that as they pass through the slope field are tangent to each one of those slopes as we go along. Because that's what this equation is telling us. It's saying that y prime, so the tangent to the curve, should be given by this quantity right here, which is what we've just plotted in this figure. So that means that solutions will look like this. So I'm trying to draw these things so that they're tangent to every little line segment that they pass through, so they're flowing along like that. Okay, so there's some solutions for this one. Let's look at another example let's take dy dx to be x minus y. All right, so again, we'll have some axes here. Maybe I'll just zoom in. There we go. And let's see. So I'm going to have my xy and my f of xy, which in this case is x minus y. Oops. Actually, I can't write as easily if I zoom in like that. Okay, here we go. So let's plot some points. So if I'm at 0, 0, then 0 minus 0 is 0. If I'm at 0, 1, then I have minus 1. If I'm at 1, 0, then I have 1. And so let's plot these points. Let's see. So what did I just find? So I've got, going through the origin, I've got a slope of 0. Going through the point 0, 1, I've got minus 1. So that's this one here. Going through the point 1, 0, I've got slope positive 1. So that's this right here. And what else do we notice? Well, in fact, if I pick any points where x and y are the same value, so in other words, anywhere on the diagonal, then I'm going to have number minus number, which is 0. So that tells me that I have 0 everywhere along the line y equals x. Okay. And then I can also see that if I move to the line 1 to the right, then for each of these, the x value will be 1 more than the y value. And so the difference will give me 1 everywhere along these points. And if I move 1 further to the right, then the difference is going to be 2. And so forth. Meanwhile, if I move back to the left, then these guys are all going to have coordinate or slope minus 1. And if I move back again, they're going to have slope minus 2. And so forth. And now I start to get an idea of what the solutions are looking like, and I can probably sketch some integral curves for them. Something like that. Okay. And so the thing that helped us speed up the graphing of that one right there is that we managed to spot some curves along which the slope is constant. And so this is called an isocline. So an isocline is a curve along which y prime is constant. And so if we go back to the figure here, then any line with slope 1 here is going to be an isocline, because the slope is going to be the same anywhere along either of those green lines. There was also, back in the first example, a very particular kind of isocline, which is called an equilibrium solution. So an equilibrium solution is a solution along which y is constant. So in other words, where y prime is equal to 0. And so you can see immediately that that's going to be a horizontal isocline. And so we had an equilibrium solution, going back to the figure here, that came right through here. Y of 0 equals 0.